Okay, in this video we're going to take one more look at circuits, and we're going to look at a combination circuit. What I mean by combination is here we have components that are in series and parallel with each other. Okay, and what I mean by that is if we take a look at this, there's obviously two pathways, but this second pathway doesn't start until after we get past the 8 ohm resistor. So all of the current must travel through this 8 ohm resistor to begin with, which means that these things right here, the combination of these, are actually in series with the 8 ohm resistor because there's only a single pathway where the electricity can go before it eventually splits to go through these two separate pathways. But there's no way for the electricity, for the current to flow through this resistor or this resistor without first going through the 8 ohm resistor. So we have this and the combination of these in series, but then obviously we have a parallel component right here where we got two different pathways. It just isn't for the entire circuit. Okay, it's for one little piece of the circuit. So the way we start into this is we're basically going to try to find the equivalent resistance. We always want to start, no matter how complicated this is, looking from the perspective of the battery. How much current is going to be flowing out of the battery? What does it see, essentially? I know the battery can't really see, but what does it feel like to the battery? Like how much obstacle is in the way, and how much is the flow of electricity sort of constricted or impeded by this combination of stuff. So what I'm going to do is I'm going to start with the parallel components. These right here that happen to be in parallel with each other. And we're going to see if we could try to kind of turn those into one single amount. Okay, so I'm going to take that and do 1 over R, and this R is going to represent the combination of these two once I put them together as a parallel situation. 1 over R equals 1 over 3 plus 1 over 5. Okay, so I'm going to go through and do that right there and just solve that. And when I solve that, and I won't show you the algebra here because you guys have been through this before, the overall resistance here is 1.88 ohms. Okay, so I know that's a 3 and that's a 5, but because they're in separate pathways, it opens up more space and more places where that current can go, and so it actually lets the current flow more freely, so there's less resistance by having more pathways. So this right here, 1.88 ohms, represents the combination of those two. However, all of the electricity must go through the 8 ohm resistor, and then it's like it's going through a 1.88 ohm resistor, even though it's two separate pathways. This is kind of what the battery sees. It sees this plus this, all as one value. So my total equivalent resistance is going to be 8 plus 1.88, which is 9.88 ohms. So when you deal with a combination circuit, you always want to start by going, what does the battery see, essentially? What does it feel from its perspective? Okay, we've got our total resistance that the battery is experiencing. Okay, now let's take a look at what we can do with that. If we have the total resistance and we have the total voltage, then it's pretty easy for us to go through and figure out the total current coming out of the battery. Okay, and the current that will be coming back into the battery should be the same. So I'm going to start by going, all right, I want current, that is voltage divided by resistance. So I equals V divided by R. Okay, and my voltage is 6 volts, and my resistance is 9.88 ohms. When I put that in, I'm going to get about 0.61 amps. Now be aware, I figured out the current. That's a rounded value. It's not exact, and so I'm going to label it as that, but that doesn't mean our check at the end is always going to come back to be exactly perfect, okay? And it's a small value, so the more you round, the more it really changes what that is. So I have 0.61 amps, 0.61 amps, okay? Now, we got to remember the special things about both parallel and series circuits, okay? So in a series circuit, the current is going to be the same everywhere, but the voltage gets divided between the components. We have a voltage drop across each one of those components. In a parallel circuit, the voltage is the same for each pathway, but the current splits at one spot, and only some of it flows through one spot and some flows through another spot. So let's take a look at what that would be. Let's start by figuring this out right here. This is easy to forget. There's a whole bunch of this 6 volts that's going to get used up essentially, and there's going to be a big voltage drop across this resistor. So this resistor and this resistor are not going to feel 6 volts of pressure or 6 volts of potential energy, because a lot of it's going to get used up and it's going to drop because of that first component that's there. So let's take a look at what that would be. Let's find the voltage drop across R1. Okay, so we're just looking right up here. Now I go back to my Ohm's law. Voltage is current times resistance. I know that there's 0.61 amps coming out of that battery, and it's got to flow through an 8 ohm resistor. Okay, 8 ohms. So I'm going to multiply those together, and this is going to tell me that 4.88 volts is going to get used up or dropped as the electricity flows through this resistor. Okay, that's our voltage drop. Okay, so I'm going to put, there's our drop. All right, so that means, let's see if I can get a different color here to write this. That means 4.88 volts. 4.88 volts of energy is getting used up just going through that resistor. That's almost all of our voltage. There isn't much left. So these over here are only going to experience a small amount of voltage or potential energy because that 8 ohm resistor is sort of using it all up to begin with. Okay? So let's figure out what those are experiencing. The remaining voltage, all right, and this is the part that's easy to forget to do. The remaining volts that can be supplied to these two different pathways is going to be what's left over. 6 volts minus 4.88 volts, and that gives me 1.12 volts. So at this point right here, I have 1.12 volts supplying energy to these two pathways. Now, if we remember some things from our parallel circuits, the voltage is the same. Each pathway gets the same amount of oomph, the same amount of push. Okay, even though each pathway doesn't look identical, they get the same amount of potential energy supplied to it. So this 1.12 volts is going to push current through here and through there. All right, we get the same amount of voltage on each one. Let's figure out how much current is going to flow through each one of these. Okay, so I'm going to look back over here. Current is voltage divided by resistance. So current is voltage divided by resistance. But in this case, it's not the overall voltage. We've dropped out a whole bunch of it because of that first resistor. It's 1.12 volts divided by, in this case, 3 ohms of resistance. Okay, if I put those together, I get 0.38 amps. Okay, and that's another rounded value. Okay, it's all right. Don't worry about it. That means I have 0.38 amps flowing through that particular pathway. Let's take a look at the other one. 5 ohms, there's more resistance. We should have less current coming through this pathway because of it. So I do current is going to be 1.12 volts divided by 5 ohms of resistance. And in this case, I get 0.22 amps. Okay. Now, let's take a look at what we have. 0.61 amps coming out of the battery. Right here, that current splits. 0.38 goes through this pathway and 0.22 goes through that pathway. But if I add those up, this one and this one, I'm going to get 0.60 amps. And you look at that and say, yeah, it's not the same as 0.61. Did we lose some energy? No. That's just a rounding difference because we have such a small value. At some point along the way, I've rounded tiny bits and pieces, and it just keeps getting me a little bit further away from the actual amount. But that's close enough. I know I've done my analysis correct. Okay? So I found out how much current flows through each pathway. I found out the voltage drop across the first resistor and the voltage remaining that pushed the electricity or the current through the other two pathways. Okay? So now I essentially know everything there is to know about this. And these two amounts come back together to form the 0.61 amps that's going to go back into the battery. Okay? So whatever leaves the battery should be coming back in. All right, and that's a combination circuit. Now they're not all going to look the same, but what you always want to start with is finding if there's some parallel components. See if you can combine them together and kind of treat them as one value of resistance. And then no matter how many of these there are, you can take a look at each one of those pathways and go, oh, okay, well, I got this plus this, and then maybe I'm adding it to something else afterwards. But you try to turn those pathways into a single amount of resistance using this formula right here. Okay? And basically just jump in, and if you understand what should be happening with current and with voltage, you'll be able to tell when something doesn't feel right. Okay, all of these different measurements should sort of tell the same story. If your two currents don't equal what comes back to the battery, something's wrong. If your voltages, when you divide them up, don't equal the original voltage on the battery, something's wrong. Okay, if you forgot to do this part, you're going to notice you have gigantic currents here, and it's not going to represent what's coming back into the battery, and you know something went wrong. Okay,